I'll explain to you like you're 12.
Okay, please. Okay. Even better. Yeah.
So approximately 13.8 billion years ago, everything that you see and interact with in this universe began in an infinitesimal point. That is the birth of the space and time of our universe. We have been expanding ever since. Now, how does something that big ever become that small? Well, it's not matter trying to occupy the same space as itself. Energy can be essentially any size compacted, and then you can measure what's there by what the temperature is. And so it's very hot fireball, basically. And as it expands, it cools, and the cooling energy makes matter. It's equals mc squared. Energy on one side, mass on the other side. This c squared is just the speed of light. It's just a constant. But Einstein came up with this in 1905, and it made so much of the universe make sense at that point. And so, and it would take a while. Do we expand? We cool enough to make stars and galaxies, and we're still expanding to this day. There are mysterious forces operating that we don't yet understand, what we call dark energy. That's a pressure in the vacuum of space, making us expand faster than what would be allowed by the collective gravity of all the galaxies. That's a frontier question that is not yet resolved. Then there's sources of gravity that we don't know what's causing it. We call that dark matter. If you add up dark matter and dark energy, it's 95% of what's driving the universe. So everything you and I know and love about the biology, chemistry, physics, astrophysics, forces, food, calories, molecules, solids, liquids, gas, it's 5% of what's going on in the universe. That's amazing. And this is why when I began, I said to you, sometimes I wonder whether we're smart enough to figure out the entirety of the universe, or do we just figure out our little fraction of it and live happily ever after within it. Now, that scenario, you have full rights to ask, what was around before that? So ask me that.
What was around before the Big Bang?
We have no idea.
Okay.
Well, we have suspicions. There might have been a multiverse, which has come out of latter-day mathematics related to quantum physics and Einstein's relativity. What comes out of those equations is a multiverse.
What's a multiverse?
It's this medium that is pumping out universes. We are just one of them.
What caused the multiverse?
We don't know.
Eventually,
it's a frontier. There's no crime in asking the question at the frontier of our knowledge. There are people who have to have answers. They don't make good scientists. The urge to have an answer can be influenced by their bias, by their culture, just take a look at all around the world, the origin stories. The origin stories flow out of the cultures from which they emanated.
What are your untested, unverified, untestable ideas about where all of this universe stuff might have gone? Because I know you must sit at home sometimes and just mull. You do a lot of mulling about the origins of the Big Bang and those things.
Well, we all do. So when you confront the unknown, you write the recipe for more data. That's all it is.
And what are those recipes that you've written?
We need a telescope. We have telescope. I haven't written. I mean, my field has written them. We have telescopes specifically designed right now to get a better understanding of dark energy and its manifestation throughout time in the history of the universe.
Explain dark energy to me like
no, it's something in the vacuum of space that's making the universe accelerate in its expansion.
Okay.
From that original explosion, we have all the galaxies, all the matter, all the gravity. You expect the expansion to be slowing down at some rate based on the gravity.
Oh, but it's speeding up.
It's like tossing something in the air. Gravity of Earth slows it down and actually makes it reverse. So we expect that. We went to make that measurement and we got the opposite answer. The universe is accelerating. That won a Nobel Prize. 1998 Nobel Prize. It's a term in Einstein's equation that he rejected. So there can't be a negative gravity. Its value in his equation must equal 0. And so let's move on. Then we discover it. We come up with a term for it. I think it's a bad term. Bad because it leaves the witness. We don't know what it is at all. So don't call it dark and don't call it energy. Call it Fred. Okay, something. And dark matter, we don't know what that is either. Okay, let's call that Wilma. We got Fred and Wilma. We don't know what it is.
So the key question I think that people are talking about at this moment in time, because you had Obama make those comments in that interview saying that he was joking. I think he was joking when he said there are aliens he's just never seen.
No. First, A, Obama is scientifically literate. It's A. B, he said, because he's scientifically literate, he said what is scientifically defensible, that there are probably aliens in the universe. Anyone who studied that problem will arrive at that conclusion.
They're real, but I haven't seen them, and they're not being kept in, what is it?
Area 51?
Area 51. There's no underground facility, unless there's this enormous conspiracy, and they hid it from the President of the United States.
That's what he said. But as former President of the United States, and we have sort of alien adjacent culture, it was, oh, that must mean there are aliens in the basement of the White House or somewhere in government custody. They took his statement that, sure, there are aliens out there and turned it onto the U.S. government. And when I heard his comments, that's exactly what any scientifically literate person would say. What people did with that information, he then had to come back and explain. I didn't even think that was necessary, but apparently it was.
And then Trump responded.
Okay. Mm-hmm.
On Air Force One in an interview and said,
well, he gave classified information. He's not supposed to be doing that. You know?
So aliens are real?
Well, I don't know if they're real or not. I can tell you he gave classified information. He's not supposed to be doing that. Well, he made a big mistake. He took it out of classified information.
Trump seemed to stoke the idea that there is aliens. And then from that, shortly after, we had the UFO files announcement.
Sure, great. Bring them out. I love
that they were going to release the UFO files. And now we find ourselves at a place where the general public is again really, really curious about the subject of aliens. And you see it on the Google Trend data, which I've got in front of me here. You see the up, the down, the up, the down based on what people are talking about. So my question to you is this central question, which is, do you believe there's intelligent life in the universe?
So one of those peaks in May, in part, was because there were files released that week by the Pentagon. And dare I suggest, my book was released in May, on May 12th.
Good timing.
Yeah, it just turned out that way. I decided to jump into the ring, not jump in, put a foot into the ring, more accurately, when I saw these high-ranking whistleblowers come forward in Congress, sworn testimony. Whistleblowers, former intelligence officers, former military folk. And I said, all right, it's time to jump in, because no longer can you discount the testimony the way you might have done so before with the farmer in the back 40, who saw something and is talking about it, but didn't take a picture of it. All right. All these testimonies that have existed in the past and accounts of UFOs, now when official government people are doing it, then, all right, it's time to take it up a notch. And what do I mean by that? Bring out the alien. If you're saying you got an alien in the shed, in the back 40, just bring it out. And the moment you do that, no one will ever have to ask again, do you believe in aliens? That's the question I've been asked. Do I believe in aliens? No one has ever asked me, do I believe in elephants? Why? Because we've shown elephants. Okay? We have elephants. We've seen elephants. So,
but do you think there's intelligent life in the universe?
I don't see why there wouldn't be, given the size of the universe and the age of the universe and the ingredients of the universe. I mean, think about it. In the early Earth, life got underway within 100 million years of as early as it possibly could have. That sounds like a long time, and it is, but that's small compared with the timeline of Earth itself, of life on Earth. It's like 5% of the timeline of the Earth. Almost as fast as it could possibly happen, the basic ingredients on Earth, which matched the basic ingredients of the universe, went from organic molecules to self-replicating life. Whatever our challenges in the lab, Earth didn't seem to have a problem accomplishing it. And so look how quickly that happened. Yes, it would take a long time, much longer, to generate what we're calling intelligent life. But given how many planets are likely in the galaxy, our catalogs now have 6,000 exoplanets in them. And that's just in a tiny little area. That'd be in a little circle, that'd be in a little, if the sun is here, do a little bitty circle around it where we've searched for exoplanets, and we got 6,000 just in that little.
What's an exoplanet?
Exoplanet, planet orbiting another star.
Oh, there's 6,000 in a little.
We've cataloged 6,000. In 1995, what year were you born?
92.
92. So you were 3 years old when we discovered our first exoplanet.
Really?
Yeah.
Wow.
And now
Blimey.
we're rising through 6,000. It was banner headlines back then, not today. But if life happened on Earth as swiftly as it did, no one among us who've studied the problem are given reason to doubt that it couldn't happen frequently elsewhere in our galaxy or in the trillion other galaxies in the universe.
This is just the Milky Way galaxy.
This is a version. Yeah, this is, if you could step out of our Milky Way, it would resemble this greatly.
This is one galaxy, right?
One galaxy containing hundreds of billions of stars. This cloudy thing, you cannot resolve the cloud into the individual stars. Galileo did this. He said, I wonder what that Milky Way is. Is that just a cloud? Took his telescope, put it on the Milky Way. He saw individual stars.
And how many galaxies are there in the universe?
100 billion stars in a galaxy, at least 100 billion galaxies in the universe.
Is the answer that we just don't know how many there are?
Let's quantify what it is to not know. In the universe, things range over such a huge scale that if you're off by a factor of 2, which sounds significant in most everyday life, but if things range over factors of trillions, then if you can get an answer within a factor of 2, you're doing really well. You have a basic understanding of structure, space, and time. And so our galaxy has several hundred billion stars in it. No, we don't have an exact count, but that's a very good estimate because we know the total mass of the galaxy and we know how much mass a star occupies. We know how much dark matter there is. So we can calculate the likely number of stars there are in the galaxy.
Planets?
So now, given our data on planets that we've obtained, we have many star systems with multiple planets. And that's just in our neighborhood. So if that's representative, then you just scale that up. So if you looked in that little zone everywhere and just up the number, you end up with millions of planets, possibly billions across the galaxy. That's how you would estimate that. So it's not knowing the exact answer is not the same thing as having no clue.
And there might be hundreds of billions of galaxies.
Yes. Not just might be. There's at least that many. In the observable universe, the actual universe goes beyond our horizon in the same way for a ship at sea. You have a horizon.
Mm-hmm.
Are you saying to yourself, well, that's the edge of the earth or that's the edge of the ocean? No. You keep sailing and more ocean comes in view.
Is it infinite?
It might be. We don't know. You're asking all good questions. And you're going right to the edge of what we don't know.
Is it possible for something to be infinite?
I'm not going to put a prerequisite on the universe that it's not. Just because infinity is kind of hard for the human brain to wrap your head around doesn't mean the universe can't or shouldn't be it. We've made assumptions about the universe just to be consistent with our own philosophies that just turn out to be flat wrong. Copernicus, a religious man, comes up with an idea that maybe the sun is in the center of the known universe and not Earth. So we go from geocentric to heliocentric. All right. Well, if you do that, then we don't have epicycles. All right. Then we just have orbits, simple orbits around the sun. Well, he did that. You know, it didn't match the observations as well as the epicycles did. So do you throw out the whole idea? No. We would learn later, 50 years later. The orbits are not perfect circles. He made them perfect circles because it's the universe. God created the universe. God is perfect. The circle is a perfect geometric shape. Clearly, anything moving in the universe is going to be in a perfect circle. That was an assumption placed on the universe derived from our own philosophical proclivities. In that case, a religiously philosophical proclivity. Mm-hmm. So, given this exercise, this failed exercise in the history of science, of which there are many examples one can give, I will not say that the universe can't be infinite.
What's in the middle of the galaxy? Because it looks like a light.
There's a black hole. Well, in this picture, the density of stars is way higher in the middle of the galaxy than out here.
Why?
We're figuring that out. We think in the formation scenario of the galaxy that most of the mass is near the center and it gets thinner as it comes out. And so we're going to have the most stars where the most mass is that you start with. So it's not a surprise that the middles of these things have the most stars because they have the most mass. And in the exact middle in the center is a supermassive black hole, which we've measured to be there. In fact, a Nobel Prize was given for that measurement.
Can you explain what a black hole is, like I'm 12?
Oh, yeah. You know, at first you got to respect black holes. Don't ever diss a black hole because you will lose. So we're here on Earth, and the old adage, what goes up must come down, you've heard that. I would learn by the time I was 9 that that's just false. No, by the time I was 10. Because I was 10 years old, because that's how old I am, we walked on the moon. And then we left rocket parts on the moon. Mm. Those are never coming back to Earth. So there are things that went up that never came back. Okay? All right. Well, what started the adage, though? Well, if you take something and toss it, it actually slows down, comes to a stop, and then speeds up and comes down again. It's captured by Earth's gravity. Turns out there is a speed with which I can throw this so that it never comes back. Let's get there. If I throw this a little faster with more energy, it goes higher before it comes back, right? How about even faster? Even faster. It gets higher and higher and higher and higher and higher. You can calculate using physics and gravity equations. There's a speed with which this will go so high up, it'll reach infinity. If it reaches infinity, it's not coming back. That's called the escape velocity for Earth. How fast is that? It's really fast. Really fast. 7 miles per second. If I throw this at 7 miles per second, it'll reach the edge of the universe and never come back to Earth. Suppose Earth had more gravity than it currently does. Does it make sense that that escape velocity would be greater than 7 miles per second? Mm-hmm. If Earth's gravity were stronger, it might be 10 miles per second, 100 miles per second. Keep up this exercise, you'll reach a point where your object has an escape velocity that equals the speed of light. The moment it achieves that, light cannot escape. It's not moving fast enough. And if light can't get out, it's black. If you fall in, you are never coming out because you can't ever reach the speed of light. There's no greater definition of a hole than that. Hence, black hole. By the way, Einstein could have predicted them, but it was too weird for him to go there with his equations. We would learn about black holes mathematically in the 1960s, make our first discovery of one in the 1970s, a famous source of X-ray energy called Cygnus X1. And now they're common, and we've even discovered them in the centers of galaxies that have like 1 million times the mass of the sun. Monstrous black holes, dining on anything that comes close.
Just things that come close.
Yeah, it's not going to reach out. So if the sun were to become a black hole now, it won't reach out and grab us and suck us in. Oh, it'll have the same gravity as a black hole as it does as a star.
But it's if you go close.
Yeah, you can get really close to it, and then you're not coming out.
Is there a certain distance? Wait.
It turns out there is. There's a distance around every black hole. I think it's called the ergosphere. It's got a name where there are no stable orbits around it. If you get closer than that, you will fall in no matter what. Whereas beyond it, you can maintain a stable orbit and look at black holes from a distance.
And where'd you go if you get sucked in?
Well,
Are you crushed or you?
Well, it depends how big the black hole is. Small black holes, that's all she wrote. Okay.
This one.
Oh, that one, you'll fall in.
And then where do I go? I'm just collapsed.
Well, there are books. I have one on my shelf, and I've even read it. It's a graduate textbook that describes the mathematics of space and time on the other side of a black hole. And it shows that a whole new space-time opens up in front of you.
What?
Inside the black hole.
What
the whole universe. The math shows that. Given the general theory of relativity, which gives us black holes in the first place, if you follow the math, you get a whole space-time that opens up inside the black hole. And as you fall in, your time changes. So time ticks more slowly for you relative to the universe. It's called time dilation. And so as you look out in the universe will unfold faster and faster and faster. And you will see the entire future history of the universe unfold as you descend into the black hole.
When you say descend, because I thought of it as like, if you go close to a black hole, you're going to be crushed into a small mass.
Well, I didn't get to that part yet. I'm describing what happens to space and time as you descend through what's called the event horizon. That's the region out of which you don't escape. That's the functional size we give to black holes. How big is its event horizon? You cross over within that volume, that's where the escape velocity is greater than the speed of light. And you're not coming in. So it has taken the fabric of space and time and folded it back on itself. So there's no pathway you can take to get out of a black hole. You're in there forever. And for the small black holes, here's an interesting fact. You don't think about this, but it's true. When you stand, your feet are closer to Earth's center than your head is. Okay?
Mm-hmm.
You can calculate what the force of Earth's gravity is at your feet and the force of Earth's gravity is at your head, and you'll get two different numbers. They're very close to each other, so we don't think about this. It doesn't matter to us.
Mm-hmm.
But as you descend a black hole, the difference in gravity between your feet and your head gets greater and greater and greater. They're called tidal forces, and they end up stretching you head to toe. And initially, it probably feels good, right? You just sort of stretch. And then you realize, oh my gosh, this is unrelenting and it's getting stronger. Eventually, you'll snap into two pieces, likely separated at the base of your spine, if you sort of look at the structural integrity of human physiology. And then you're still falling, and now those same tidal forces will operate on your torso and on your lower half. They'll stretch and they'll snap into two pieces. So you go from 1 to 2 to 4 to 8 to 16, and you'll bifurcate in pieces all the way down to the center of the black hole. The worst part is, well, maybe equally as worse, is you are occupying a narrower and narrower volume of space-time as you go down to the singularity that is the center of the black hole. So not only you get stretched head to toe, you're getting extruded through the fabric of space like toothpaste through a tube. Have a nice day. So, yeah, you don't want to test. All of our equations tell us that's what will happen to you.
What's at the heart of the black hole? You said
we don't know. So here's a problem. General relativity that gives us the black hole in the first place. If you follow the equations, the center of the black hole is infinitely dense and infinitely small. How does that even happen? We don't know. Maybe something prevents that. But that is the limit of Einstein's general theory of relativity.